of the school year, we talked about kinematics, right? And motion. An object in motion wants to, in a what? In a what? In a straight line. Okay, good. So when the object moves over time, we call that displacement. So it started here, and then it moved to here, right? That's displacement over time. Now that change in position over time is velocity, right? And Mr. Adams could probably, because it goes from 0 to a velocity, there's a change in velocity, and that change in velocity is acceleration. And the car has a mass, right? And when I apply an acceleration to a mass, that's a force, right? Now, I'm cheating a little bit. We're letting gravity pull the car down, right? And we talk about that too. For roller coaster design, we have a potential energy when the cart's up here. Earth is pulling on this mass right now, and as soon as I let go, boom, it accelerates and moves. Okay? Now, all this stuff is on a straight line, but for circular motion, the way that we study and observe this behavior will now be closed. And to make things easier for yourselves, we're going to do uniform circular motion, which means, well, I'll explain that in a second. But basically, the cart's still moving on the track. It's just now its path is restricted, right? Is velocity a vector or a scalar? Vector. What does vector mean? Has a magnitude and what?
Direction.
Direction. What do you notice about circular motion? What's this car doing? It'd be very difficult for Mr. Adams to do, but if I were to spin the motion of this car where the speed is the same, is the velocity changing?
No.
Yeah. It's constantly changing direction. Look at that green car. Does it go in the same direction? No. It's constantly changing direction. So the speed may maintain, but the direction is constantly changing. Therefore, the velocity is changing. And if the velocity is changing, then what? We have acceleration. Does that make sense? And if we have the acceleration of an object that has a mass, then we have what?
Displacement.
Displacement, but force, right? Mass times acceleration is force. And if we have force that's done on an object, what's that called? A force moves an object a distance? Work. And if we do work, we're using energy. So all those things are related, but now we have to consider this: how do you calculate, how do you track a change in velocity when the magnitude stays the same? So that's what we're going to talk about. Okay? But in order to do that, we really kind of have to understand angular measure, angular speed, and velocity, uniform circular motion, and centripetal acceleration, angular acceleration, and then these two are my favorites. Those are going to be a lot of fun. But Newton's law of gravitation and Kepler's laws of Earth and satellites. Did you guys know that there are thousands of satellites above our heads orbiting the Earth right now? It's kind of congested up there. So let's talk about angular measures. Well, if I draw a circle on the xy plane at the point P, normally this point P on the xy plane is x comma y. But if I take that point that's on a circle, by the way, a circle by definition is all the points equidistant from the center. We can describe this position of an object by using polar coordinates. In other words, we can calculate the radius and the angle. If I come from the standard position here, which is 0 degrees, or 0 radians, and I move an angle of theta, right? You guys remember that this is the Greek letter theta? In other words, I swing that around a certain amount and I know the radius. I can also determine this point. That's another way to measure the point. So we can think of it in terms of x comma y, or we could think of it in terms of r comma theta. Okay? Now, truthfully, we'll do a lot of x comma y. So what does that mean? Well, that means that x should be equal to r cosine of theta, and y is equal to r sine of theta. Where that comes from is our trig functions, right? So I have this xy plane. I draw a right triangle. This is the point P, which is normally x comma y. But the x is really this distance, isn't it? How far we move over horizontally. And the y is this distance, isn't it? Yeah? And then I have r here, which is the radius of the circle, right? If I think of this whole thing as a circle, that's the radius of the circle. And I have an angle here. Well, that's the trig function, isn't it? Isn't sine of theta equal to the opposite over the hypotenuse? Well, what's the opposite? Y. What's the hypotenuse? R. And if I multiply both sides by r, that's what I get. Does that make sense? And the same thing with cosine. Remember that cosine of theta is equal to the adjacent, which in this case is x, over the hypotenuse, which is r. And algebraically, if I multiply that through, I get that. Does that make sense? Any questions? So it's just basic trig. Now, do you have to draw that out every time? No, you don't have to. You could just memorize these two things here. So then, one way that we can measure the angle is there's this relationship between the arc S, arc length S, the radius, and theta. Now, this kind of looks like an O, and Mr. Adams always remembers this relationship by remembering the phrase standing room only. Standing room only, that's how I remember it. Arc length is equal to the radius times theta. Now, one thing I want to point out is that the angle is always in radians. Okay? Always in radians. Now, to the right, I've got some conversions. Okay? 360 degrees is equal to 2 pi. 180 degrees is equal to pi. Now, if you know that relationship, you can always find it by setting up a proportion. Do you guys remember how to do that? No? Yes? No? Let's clear this out. Let me show you. If I said pi over 4, that's a radian measure. And the relationship is 45 degrees equals pi over 4. So I know that 180 degrees is equal to pi radians. Now that can be written as pi over 180, or we can think of that relationship as 180 degrees over pi. So if you were to say, Mr. Adams, I want to know what 45 degrees is in radians, how would you do that? Well, you set up a proportion. I would say pi over 180 degrees is equal to something over something. 45 degrees is degrees. Where are we keeping the degrees? On the top or the bottom? Look at right here. Which one is degrees?
Bottom.
Bottom. So I put 45 degrees here. What is the radian measure? Do we know? No. What do we put for things we don't know?
X.
X. And if you cross multiply that, you get 45 pi is equal to 180x. And technically you get 45 degrees and 180 degrees. What would you do next?
Divide both sides by 180.
Divide both sides by 180. degrees, 180 degrees, and guess what? The degrees cancel. Anybody want to take a guess what 45 over 180 reduces down to?
4.
1 over 4. So I've got 1 over 4 times pi, or pi over 4. Does that make sense? You want to write this down in your notes, okay? Because you're going to do that for homework problems. All right? I'll give you guys a second to do that. So, the relationship between the arc length, the radians, and the angle theta is this. When this cart moves, it's moving. What is it moving? It's moving a position on this track. Right? Well, if it's moving a distance across this track, when I take the track and make it into a circle, now what is the cart moving? It's moving a length, but a very specific type of length. An arc length. Do you guys see that? It's moving an arc length. And so because it's moving an arc length, I can do some math here based on the radius or the angle. Does that make sense? Can I clear this off now? Yeah? All right. So then angular measure is any variation of that. And so we said that sine of theta was the same as y over r. We said that tangent of theta is y over x. This is that formula rearranged, the s equals r theta. If you rearrange it, theta equals s over r, right? So it's just an algebraic manipulation. But a small angle approximation is very useful, and it allows for the substitution of theta for sine of theta when the angle is significantly smaller. When theta is really, 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 really small, we could approximate and say that theta is approximately the same as y over x. When it's really, really, really small. Does that make sense? And the reason for that is that s over r should be close to y over r, which is technically pretty darn close to y over x. And what they're saying is, here's your r, and here's your x. And when it's really, really small, and you say, well, Mr. Adams, what do you mean here's your x? Well, look at this. The x value goes from here to here. See the x value here to here? See, this is a larger angle theta. When theta is really, really small, the x value is almost the same as r. Do you guys see that? The length that we've drawn? Does that make sense? Okay. Any questions on that? So probably in your homework you'll have 1 or 2 questions where they're not going to give you all of the information, and you may need to use this.